Good day to all. So, in today's session, we are going to see about BJT, biasing, Q point, and the stability factor. So, what is BJT? BJT is bipolar junction transistor. We all know that it's a two junction device with three terminals, namely emitter, base, and collector. So, let us see a brief overview about the BJT, its construction, considering NPN transistor, emitter region consists of majority charge carriers as electrons, base is made of p-type semiconductor which has holes as majority charge carriers, and collector region which has again electrons as majority charge carriers. These are the three terminals. So, let us see in short the operation of this NPN transistor. So, as this emitter base junction is forward biased, the electrons present in the emitter region will get repelled by the negative terminal of this forward voltage, so that all the electrons will move towards the base. And since the base is lightly doped, not all the electrons will find holes for recombination. Only few holes will have space or to accommodate electrons that is coming from the emitter region. So, the remaining electrons will move towards the collector. So, this electrons that has to be collected in the collector region can be done by applying a reverse potential across collector base junction. So, if you take the current equation of this BJT NPN transistor, IE is equal to IB plus IC. What is IE? It is a current due to the flow of electrons from the emitter towards the base. And few electrons here will get recombined with holes constituting base current. The remaining electrons will reach the collector that constitute the collector current. So, IE, the total current, is equal to the sum of the two currents, base current and the collector current. If you take the direction flow of this currents, IE will take this direction and IB will take this direction and IC will take this direction. And as we all know, the conventional current direction is opposite to the flow of electrons. So, all these parameters, they denote the conventional currents. Now, coming to the characteristics of this device, the BJT NPN transistor, as we talk here, can be characterized based on two graphs or characteristics curves. One is the input characteristics. That is drawn between emitter base and base current. If you take the input characteristics, as this base voltage is increased, the base current will also increase till a point called cut-in voltage. This is equal to 0.7 if I use the material silicon to construct the transistor. So once it approaches this cut-in voltage, the transistor base current will start increasing rapidly. So if you observe, the range of this base current will be in the order of microamps. Why? Because if you take the base region, it's very lightly doped and it has got only few holes available for recombination with electrons, constituting the base current. So in the transistor, always this base current will be in the order of microamps. Okay. So this emitter current will be in the order of milliampere, base current will be in the order of microampere, and this again collector current will be in the order of milliampere. Okay. Right. So next comes the output characteristics. Output characteristics of this BJT. So it's a graph drawn between collector to emitter voltage and collector current. Collector to emitter voltage is in the order of volts and collector current is in the order of milliampere. So this output characteristics has to be found based on the input conditions. So for any fixed value of base current, we are going to see the variation of this collector current with respect to collector to emitter voltage. So if you observe, for IB equal to 0, which means without any input given to the base and emitter junction, my base current will be 0 microampere. So with this condition, as I increase my collector to emitter voltage, I have some small current Actually speaking, without the input, I should not get any current at the output terminal. But why? Because here I get small amount of current. It's because of minority charge carriers. Okay. So this current is contributed by minority charge carriers. So now as I increase my base current, say to 10 microamps or maybe 20 microamps, my range of current will increase. Okay. So this is the value of collector current at say IB equal to 10 microamps, and this is the value of collector current say for IB equal to 20 microamps. So this is about a basic overview of BJT. Now what is biasing? Biasing is the process of application of DC voltage in order to maintain proper value of collector current and collector to emitter voltage. Now we'll see what is biasing. Biasing is the application of DC voltage in order to maintain proper collector current and collector current say IC and collector to emitter voltage, that is VCE. So what do you mean by Q point? Q point is this value of collector to emitter voltage and collector current. Why do we focus on this Q point is, it is only this Q point that defines the proper operation of the device for any specific application. So again, this is always done considering the output characteristics of BJT. So as we see, VCE, IC, the output characteristics of a BJT. As I say, consider the Q point lies somewhere here, which means this value of collector to emitter voltage and this value of collector current is what you say it as Q point or quiescent point. Why it is called as quiescent point? Because for any specific voltage, say VCC, for any specific voltage, say VCC, this collector current and collector to emitter voltage will be fixed. So now, based on the location of this Q point, say here, this, consider this may be the first location, consider somewhere here, say this is like maybe another circuit which has a Q point of say Q2, you consider this to be VCEQ, this to be ICQ. In order to differentiate, I simply add a suffix here, VCE2. So what you are able to see the change here, if you take this device which has a Q point, the value of collector to emitter voltage and collector current lies exactly in the middle. If I take this as my Q point, see here the range of voltage and the range of collector current that the transistor has. Okay. So it is this range of voltage and current will differentiate or will say what exactly the transistor contribute. Okay. If you take for example somewhere here which has a Q point of Q3, say VCE3 and the collector current say IC3. So we have here denoted three possible quiescent points. One is exactly the middle, the other one somewhere on the top, the other one somewhere on the lower region. So if you take this Q3, the range of voltage is higher, but the collector current is minimum. So based on this location of the Q point, the application for which the transistor can be used will be different. So one is, if you take the applications of BJT, I can use BJT as an amplifier or as a switch. சார் அங்கே ரன்னிங்கில் இருக்குது, கட் பண்ண.
வெயிட் பண்ண 1 மணி நேரம் நாங்கள் முடிய பிஇபி பிறந்த ஓடிக்கு
If I fix the operating point of my BJT exactly at the middle, then I can use the BJT as an amplifier. If I want to operate the BJT as a switch, then I need to operate the BJT in 2 different states. If you take switch, it has 2 states. One is on, the other one is off state. So if I want to switch on, then I need to operate the BJT with Q2 operating point, and if I want to switch off, then I should choose this range of operating point. If I want to use the BJT as an amplifier, then my operating point or the range of voltage and current must always lie in the middle of the output characteristics. So, middle of the DC load line. What do you mean by DC load line? DC load line is the line connecting all the points, possible points of collector current with respect to collector to emitter voltage for a given VCC. So, that is what DC load line. So, this DC load line if you take, you can draw the DC load line for any given biasing circuit. So, if you take this point is said to be VCE cutoff, and this point that's lying on the y-axis is your IC SAT. The line joining these 2 points will give you the DC load line. So, in detail, what is this VCE cutoff and what is this IC SAT? IC SAT is the maximum collector current for any given biasing circuit. VCE cutoff is the voltage across collector to emitter voltage when the device is in off condition. So, if I join these 2 points, then I get a DC load line. So, if you take or consider any points that is lying along this line, it shows all the possible operating points for any given biasing circuit. So, where this is one extreme and this is another extreme of the biasing condition. So, in other words, now we are going to see, in other words, the various operating regions of the transistor. So, considering the output characteristics again, all this shaded portion will be a cutoff region, which means if I am going to operate the BJT for this minimum value of base current or even zero base current, I'll get very small collector current which is due to minority charge carriers irrespective of any value of VCE. So, very small means it is in the order of microamps also. Actually speaking, there is no current due to majority charge carriers. Okay. So, this condition is what you say it as cutoff condition. IC is almost equal to 0 milliampere because we say that there is no current due to majority charge carriers. Okay. So, this is the current in the cutoff region. I have another region which is saturation region. So, this entire range of current for some small range of VCE, you say it as saturation region, where I get for any given input conditions, I will get maximum collector current. The collector current will be maximum for any condition, which means the transistor reaches its extreme condition contributing maximum magnitude of collector current. So, this is saturation region, and this entire region you say it as active region. So, what will you say about active region is the transistor will behave in a linear manner. If you take cutoff region, the transistor collector current is completely off. If you take the saturation region, the collector current is maximum. If you take this active region, the collector current is proportional to the base current. If you take this point, say for 20 microamp of base current, I will get this much amount of collector current. If I increase my base current say to 30 microamps, I get a maximum value of collector current, say this much amount, which is greater than this. If I am going to reduce the base current also, somewhere here I will get the collector current. So, in this active region, my collector current will be proportional to the base current. Okay. So, coming to this operating region, there are three operating regions. One is cutoff region, next one is saturation region, finally active region. So, if I want to use BJT as an amplifier, I need to operate the BJT in active region. If I want to operate the switch, that too in on condition, I must operate the transistor in saturation region. If I want to switch off the transistor, then I must operate the transistor in cut off region. So, it is based on the application we are going to define, or we have to define the value of voltage, that is collector to emitter voltage, and collector current, which will define the Q point. So based on this value of Q point, it will be located in my characteristics of BJT, output characteristics of BJT. So which says indirectly what the circuit is for or what the application is. Or vice versa, if I want to use the transistor for an amplifier, then I must have this range of voltage and collector current. If I want to simply use a transistor as a switch, then I must operate the transistor within this range of voltage as well as this range of voltage, because switch always it has two state, on and off. So the voltage and current must be changed alternatively. Only then you will have both on and off state in using that circuit. So next comes the stability factor. Yes. So before looking into this stability factor, we must understand what is thermal runaway. So if you take any device, say BJT, this is the symbol of BJT, as we all know, base, collector, emitter. This is of NPN type. Okay. So now we'll see what is thermal runaway. See, if I have a transistor, say BC107, it has its own operating conditions, which means any device will be specified with its operating temperature. Why this specifications are important is the performance of the device must not be compromised. In detail, if this transistor is used under say 30 degrees centigrade and as well as say 55 degrees centigrade, there must not be any change in the value of current or voltage. But as temperature increases, the electrons within this device will get excited always, because increase in temperature will increase the heat that enhances the movement of electrons. So which changes the current that is flowing through the device. So thermal runaway is as the operating temperature is increased, we will have a very large increase in the movement of charge carriers, contributing large value of collector current, which may exceed the safe operating collector current or operating conditions of the device, that may lead to the breakage or burnout of the device. So if you take this normal NPN transistor connected in CE configuration, its emitter current is equal to beta times IB plus 1 plus beta into ICO. So this is my total emitter current, and this is the value of current due to majority charge carriers, which is beta times IB, and this is the current due to minority charge carriers. So this minority charge carrier will respond to the increase in temperature compared to the majority charge carriers, because majority charge carriers will get influenced by the input voltage. So if you take this ICO, this ICO is always temperature sensitive. What is this ICO? ICO is the current due to minority charge carriers, and that is amplified by 1 plus beta times, multiplied by 1 plus beta times. What is beta? Beta is the current gain of CE transistor. So if you take this ICO, how it responds to temperature? This ICO doubles for every 10-degree rise in temperature. So if I have 10-degree rise in temperature, this ICO doubles. If you see this equation, if it is double, that will be multiplied by 1 plus beta, which gets added to the current that is due to majority charge carriers. So you will have high impact over the total emitter current. Now we will come to the stability factor. What is stability factor, or what is bias stability? Bias stability is the ability of the biasing circuit to maintain fixed value of collector current and collector to emitter voltage, irrespective of variations in the temperature. So if you take this bias stability, you have actually 3 stability factors that can be defined. Let us also see what are the factors that affects the stability factor. See, we have seen that increase in temperature will affect ICO. So ICO is one of the factor. The other factor is beta, and another factor is VBE or IB. So these are the 3 factors that affect the current. Sorry, this has to be collector current. So there are 3 factors that affect the stability of this transistor in the biasing circuit. So if you take S, it is dou IC by dou ICO for a fixed beta or VBE or IB. S dash. S dash is dou IC by dou beta for a constant ICO and VBE or IB. S double dash is dou IC by this is S double dash, this is S dash, dou IC by dou VBE for a constant ICO and beta. So for any biasing circuit, we can find these three stability factors. So when I want to find the change in collector current due to change in ICO, the other two factors must be treated constant. So for any biasing circuit, we can find out these three stability factors by which you can assess the stability of that given biasing circuit. Considering the expression IC is equal to beta times IB plus 1 plus beta into ICO. So here I am going to find out the stability factor S. So differentiating this expression, what is this expression actually? It is the collector current for CE transistor. This is the collector current for a CE configuration transistor, where collector current is contributed by the majority charge carriers and the minority charge carriers. So differentiating the above expression, with respect to IC. So though it is actually 1, that's equal to beta into dou IB by dou IC plus 1 plus beta into dou ICO by dou IC. So 1 minus beta into dou IB by dou IC is equal to 1 plus beta into dou ICO by dou IC. So if you see this expression, this ratio is 1 by S. See here the definition. Stability factor is differentiating the collector current with respect to ICO. So this ratio I can write it as 1 by S. So 1 minus beta into dou IB by dou IC is equal to 1 plus beta into 1 by S. So from this, what is S? S is equal to 1 plus beta divided by 1 minus beta into dou IB by dou IC. So this is the general expression for the stability factor. So for any biasing circuit, if I am going to find this dou IB by dou IC, substituting the value of this dou IB by dou IC, I can find the stability factor for the respective biasing circuit. So with this, we'll end this session. Thank you. Sir? Emmanuel sir? முடிச்சிட்டேன் சார்.